There we go. So welcome to the fall K-INBRE seminar series. We have the Data Science Core presenting for us today, which is one of the main cores of the K-INBRE. And they are going to chat for an hour or so. If you have any colleagues that weren't able to join on, like I said, we are recording, and this will be posted on the K-INBRE website under the undergraduate drop-down menu if you have anyone that wants to check it out later on. So welcome to Brad and Devin.
Sounds good. Thanks, Claire. And yeah, today myself and Devin will be talking a little bit about, I'll talk a little bit about the data science core, and then we're going to just give you some project vignettes about things that you could do with data science type approaches, and hopefully you'll find it interesting. So I always like to start with what data science is. Basically, data scientists are crucial in turning data into insights. They drive scientific progress and solve complex problems. As I'm sure many of you are aware, we're basically in an age of a data deluge, primarily driven by omics technologies, but other technologies as well. And so increasingly, data scientists are playing really critical roles in biomedical research. It's a combination of technical skills and scientific domain knowledge to extract value from data. And I will emphasize the fact that when you're talking about training for a career in data science, there's a huge emphasis on technical skills. And while those are important, I think it's often lost that, especially in the biomedical sciences, that domain knowledge is really critical to being able to interpret what you're doing. And if you're paying attention to what's going on with AI, or what we call AI, this is actually becoming one of the key limiters of that technology advancing forward, is that domain-specific knowledge. And I will point out data science is kind of a superset of bioinformatics and other related kind of bioscience-specific types of approaches to analyzing data. So it's a lot more general. It deals with different types of information, but it would be considered a superset. So biology and biomedicine are data-driven sciences. We all know this. That's basically what we do as scientists. We generate data and test hypotheses with different types of data. This graph here I like quite a bit because these large innovations that are coming in biology are coming from these data science and formerly bioinformatics approaches. And increasingly now in the last 2 years, I think I've seen about the most progress I've ever seen and kind of the more data-driven approaches being driven by what we call artificial intelligence, but is basically data science. And so this is just a quick look at scientific progress, so trends in biology related to AI. You could see that publications are taking off at a very rapid rate as of 2022. And this is starting to almost look like climate change at this point, with the rate of AI-related publications really taking off in the last 2 years, with AI becoming much more accessible. Research funding is also going up quite substantially for anything that uses artificial intelligence. It's increasingly being recognized that it's important. And in particular, I want to point out the other thing is that the one field that has not really been cracked at the moment by AI is medicine. That's due to a lot of reasons, but it is kind of sitting there as one of these fields that is really looking to be disrupted by the data sciences and AI. And so you can see here, if we start looking at the data creation overlaid on the graph that I just showed you, you can see that the reason why it's really primed to do that is because you can see that the data being generated, again, is going up quite remarkably as of 2022. And I'm sure as we start getting data from 23 and 24, this is going to be even quicker. I won't go over all the details of these. These are just science and nature. AI is changing everything about science these days, especially biological sciences and biomedicine. It's even the Nobel Prize for this year. So AlphaFold generated the Nobel Prize this year. So this is AI is here. It's here to stay. And not only is it here to stay, it's really making these major impacts on the biological sciences. It's also, like I said, primed to disrupt the healthcare industry. AI is really like being recognized as a way to get around the people bottleneck, both in diagnostics and in other personalized medicine. And it really is going to change how we approach medicine, both as a patient and as a practicing physician. And I know a lot of K-INBRE trainees are interested in health careers. So this is definitely something to be aware of as you're progressing through your career. Data science careers in biomedicine is very strong, both in academia and industry. You can basically find a job right now. I get constant calls from people in the biotech industry and from recruiters looking for applicants. Our typical masters in data science are looking at 90 to 160K per year for an average or for an interquartile salary range. So it's pretty reasonable for expectations in the region. Those with PhDs and postdocs in data science, and especially that are able to do that part that I talked about, which is generating domain-specific knowledge, are really able to generate substantial salaries. So again, the interquartile starts around 100K and can go up to about 460,000 or more. This is really being driven by the fact that there are not enough people with domain knowledge at the PhD and postdoc level to go to biotech and implement these sorts of things. There's a lot of people who can go in there and do technical skills, use an LLM to interpret data, but that domain-specific knowledge is really what drives salaries. Faculty academia is becoming an essential role for all proposals. Both NIH and NSF have very specific directives to build on data science skills in the future. And so these are being looked at as being essential parts of both the training and research components of research grants. So you can go to NIH or NSF's website to learn about these, but they are very keen to implement these technologies very quickly. And again, you'll kind of hear both terms. It's kind of settled in on artificial intelligence these days. Really what most people are talking about when we're talking about AI is data science. I prefer that because the science part of it is so important, but those are basically the same things. Programming and data science is also becoming a lot more accessible, which is why, again, the technical skills are not such a big issue anymore. So the large language models like ChatGPT, Bard, or whatever they're calling it these days, Gemini, really are changing biomedicine in the fact that people that before had this huge barrier to entry to be able to do data science approaches no longer are having those technical barriers to be able to program or analyze data or wrangle it. These are now integrated tightly into the programming environments that you use for bioinformatics. ChatGPT is the most famous one, obviously, but you can tell ChatGPT, hey, I've got this type of data, it's structured this way. Can you help me out with some programming? They can edit your programming for you. So there's no more limits to getting into the data science in terms of like technical skills for programming. It's now being limited more by again, the domain knowledge. So again, being a K-INBRE trainee is a perfect time to get that type of domain-specific knowledge. So understanding the science, how to interpret the data is really important. So K-INBRE, as of the K-INBRE 5 renewal, transitioned their bioinformatics core to a data science core model. So we were basically kind of a federated type system. So I lead the entire data science core from Kansas State University. We also have satellite campus leaders. So that would be Stuart and Devin will be talking here in just a moment. And basically what our mission is we support data science in the K-INBRE system and kind of also as a indirect effect, the state of Kansas in general. So we support training, project assistance. We have grants that we support with for basically anybody who is vaguely affiliated with the state of Kansas or K-INBRE. And we really emphasize that you don't have to have a specific K-INBRE grant. You don't have to be funded specifically to do something. We can usually step in most cases and help with training and project assistance and so on and so forth. So if there's somebody out there that's got an idea or wanting to put a grant in or has a paper where they're struggling to analyze some data, all three campuses are more than willing to step in and help both with assistance, and we can also do projects as fee for service depending on the scope and nature. So definitely reach out to us if you personally want those type of services, training in particular, and services also as well. There's a lot of also opportunities for K-INBRE trainees. So for undergraduates, don't need prior experience. We are going to start funding a 4+1 dual enrollment program where you can do a BS and master's concurrently. And so you can do it in 5 years instead of the typical 6. We are working at the moment to get this streamlined in the K-INBRE system. Only certain campuses are streamlined at the moment, but I think we have the rest of them getting closer. Basically, what we just need to make sure you do is you take some prerequisite classes. And so I'm currently helping one student at KU with this because they weren't primed for the to have the prerequisites. So we're working on that. In the next 2 years, probably it'll take to get all these campuses streamlined to have that prerequisites for the 4+1. Really, the only requirement is that you participate in K-INBRE training programs. We'll have an application process that'll be opening sometime soon for this to support a number of participants. Participants at the smaller universities will be able to take more of students into the program. There'll probably be some collaboration with the main campus core leadership, so either KU, KU Med, or K-State. We also have Data Science Scholars program that's kind of adjacent to the K-INBRE Scholars program. So if you're doing a data science project, this is a good thing to apply for. I believe each of the campuses have a Data Science Scholars possibility. And yeah, these are definitely really good things to get that training that you need to get the technical and domain-specific skills that you need to have a career. And again, if you're doing this 4+1 program or considering this, this is, if you're, say, a sophomore or junior right now, you're looking at, making a pretty good salary and a pretty good career inroad in about 3 years from now. So it's a pretty good value. And especially if you are awarded the 4+1 scholarship to do this, that's again going to save you $22,000. We're starting to launch our internship programs. We're trying to work with regional biotechs to get internships that are available to you so that you can work in industry and get some industry experience before you actually graduate. And I will also mention that we do a lot of personalized training. So we have a lot of students and faculty that come to us and say that, a trainee needs to learn something, and we can develop customized trainings and help supervise your progress through learning data science. So definitely reach out. You can always reach out to me and I will figure out the best way forward depending on what your needs are, what your location is, and if we have one of the satellite campuses work with you. So yeah, definitely reach out anytime that you have questions about training. Graduates and postdocs, again, no prior experience. We do all the training. Almost all of our work at the graduate and postdoc level is personalized training. It's almost always project specific. So if you have a project where you're wanting to learn these skills to apply them, we'll generate a personalized training program for you. We'll work with you, take you through. We've all got technicians at the satellite campuses that can help you with some of the stumbling blocks that you'll run into. We typically will do this as a fee-for-service arrangement. We've got a couple different ways that the satellite campuses do this, but we will always get you started for free. It's relatively straightforward to do. And again, we're working on getting our internship program going so that you'll be able to apply for that and hopefully work at a couple regional biotechs. And again, we're trying to get practical industry experience. Same thing for faculty. I will point out for faculty, DSC PY grants are about $30,000 per year. 10K of that goes to pay for your data science core usage. The spring summer grants and pretty much all the K-INBRE mechanisms have DSE support implied within them. So definitely reach out to us if you're planning on putting in one of these K-INBRE grants mechanisms. We are more than happy to help you before and then obviously after the award. We do personalized training, almost always fee-for-service, and fee-for-service work is available if you have a grant that's currently funded and need to make progress on it. We can arrange for on-site training and workshops. And then we're doing a lot of curriculum design right now for satellite campuses to help assist the campuses get ready for the 4+1 concurrent BSMS. And always reach out to us if you need help. We're more than happy to help. So I'm going to go and skip past this in the interest of time because you can look this all up. So all the different facilities, and go ahead and ask if there's any really quick questions. And if not, I will hand it off to Devin before coming back.
You're on mute, John.
Thanks for catching that.
Did you happen to mention that we're going to be able to help provide some funding for PUIs for these fee-for-service deals?
Yep. So we will be doing our best through the K-INBRE grant to help support the fee for services that are needed to support the facility. We do as much as we can for free, and then we kind of go from there.
Yeah, because we want you guys to use these things. So,
Yeah,
all right,
and definitely
thanks.
ask, like, if you've missed a deadline or whatever. We can't guarantee anything, but we are always willing to find a way to help you to get the progress you need to make. So it never hurts to ask. I don't think we've really said no to many people at all. We've always been gone out of our way to help people. All right, Devin, you want to jump in and give a overview of a project?
Yeah, sure. So, Brad, are you speaking after me, or am I just giving the presentation and we're just kind of opening it up for questions?
I think we'll just have you talk and go for questions. I think that'll get
Right.
us on time. Because if not, I'll ramble on for another 20 minutes about something. And I'm sure there's a lot of questions out there and interest in wanting to do this. So
I'm gonna share my screen. Hold on. I'm only working with one screen today, so um can you all see this okay? Is it like in the right view? Is it in the presenter view, or are you seeing?
Yeah, it looks good, Devin. There's just a Zoom pop-up at the
Oh,
front. So
Zoom
yeah,
pop up.
yeah.
I'll just allow that for 1 month, and then they'll see me
Okay.
again in a month.
You're all
We'll do
set.
the same exact thing. Hey everyone. I just want to kind of begin by thanking Claire and Hayata for organizing these seminars and for the opportunity to speak to you all today. I also want to thank Brad for giving a really nice introduction of the data science core, kind of setting the foundation that we can build off of in this presentation. And then finally, to all of you undergrads for the hard work that you're putting in and for taking time out of your day to come listen to us talk about data science and what we do in the core. So a little bit of background about me. So I'm a professor in the Department of Biostatistics and Data Science at the University of Kansas Medical Center. And in addition to that role, there's a couple other hats that I wear at the institution. I serve as the Associate Director of Research Operations in my department. I'm the Assistant Director for Shared Resources for the University of Kansas Cancer Center. I also serve as the co-director of the BISR, the Biostatistics and Informatics Shared Resource, which is also part of the Cancer Center. I direct the Quantitative Omics Core for the KIPM, which is the Kansas Institute for Precision Medicine. And then I have a role here with K-INBRE as being one of the site directors for the Data Science Core. So a lot of different hats, but there's a commonality to all of these different roles. In these roles, I help to facilitate the delivery of data science support, or am directly involved in providing that data science support to researchers, staff, students, investigators that are affiliated with these different centers. So I get to work with a lot of different types of people on a lot of different types of projects. Most of the projects that I work on are in the realm of omics. So I apply data science methods to large-scale omic data types. That could be transcriptomics, epigenomics, metabolomics. Sometimes researchers are interested in developing prediction models on the basis of those data types for predicting who's likely to respond to treatment or not. Or are there patterns of these various molecular data types that discern different states of disease? So my segue into machine learning, which I'll define more formally in the next slide, kind of happened when I was a graduate student. So this was about 15 years ago. I was involved in some work where we were applying machine learning methods to molecular data types, primarily epigenomic data, of individuals that all had the same clinical diagnosis. So they all had the same type of cancer diagnosis. And what we were trying to discern using machine learning is, were there patterns based on the molecular data that would distinguish individuals that were likely to have more favorable outcomes? Because we know with chronic diseases like cancer, some people respond better to treatment than others. Some people progress more quickly. Were there patterns in molecular data that could tell us in advance who's likely to progress or who's unlikely to respond to treatment? And so that was my kind of entry point into machine learning. And I've continued to kind of be involved in that work throughout my career. Up in the top right-hand corner is a news story that was written when I was a postdoc. and then all the way to the present day. That picture in the lower right-hand side was taken this summer at the Cancer Center Cancer Biology Program meeting, where an undergraduate that I was working with from UMKC presented some work on deconvolution methods for DNA methylation data. So machine learning is a subfield of AI, which Brad talked about extensively. And if we were to define machine learning by Oxford Dictionary's definition, it's the use and development of computer systems that are able to learn and adapt by using algorithms and statistical models to analyze and draw inferences from patterns in data. So I highlighted a few key terms there because they kind of relate to the expertise from a technical standpoint that is needed when we are doing data science or we are doing machine learning. So really, machine learning, the way that I view it, is it's at the cross-section of both statistics and computer science. So to be an effective data scientist and implement machine learning methods, you kind of need to have a little bit of both. At a minimum, you need to have some statistics background because underlying a lot of these machine learning models, they have their origin in statistical models. You also need some computer science expertise to program and implement those models using computers. So with that in mind, there are really 4 branches of machine learning that I'd like to draw your attention to. There's what we call supervised machine learning, which is where we use labeled data. And typically with supervised learning, we're interested in making some prediction or classification. So an example of a supervised learning problem would be if we had a group of individuals and we knew which ones responded to treatment and which ones didn't. And let's say we collected some data on those people. Maybe we took a sample of blood and we used that to profile some biomarkers. In a supervised learning problem, what we would be doing is trying to use that labeled data, who responded to treatment, who didn't, to discern patterns in their biomarker data to understand the likelihood of response to treatment. So that when we are confronted with a new patient for which we have yet to observe whether they respond or don't respond to treatment, but we have their biomarker data, we can make an informed prediction about their likelihood of responding. Okay, so the key thing with supervised learning is that we have labeled data. We know who's diseased or non-diseased. We know who responds to treatment or doesn't respond to treatment. That contrasts with unsupervised learning, where we don't have the label. So an example of that would be we have a group of individuals that all have the same clinical diagnosis. They all have the disease. And what we might be trying to do is to cluster, if you will, those subjects based on some type of molecular data or clinical data that we have collected on them, and then later determine whether or not the clusters or groups of people that we've discerned, whether they're clinically relevant. Does this cluster progress faster than this cluster? Does this cluster respond to treatment better than this cluster? Key thing here is that we don't know the labels in advance. So semi-supervised kind of puts these two together. It is a set of problems where we have both labeled and unlabeled data. So we're leveraging the data that we have labels on to build, guide, prediction, and classification models. And we're using the unlabeled data to really help us understand the distribution of whatever type of data it is that we have, whether it's molecular data or clinical data, epidemiologic data, or otherwise. And then finally, we have reinforcement learning, where we have a machine that interacts with the environment, and that machine receives rewards or penalties and adjusts its behavior depending on those awards or penalties. So an example of reinforcement learning would be like robotics or gaming. So for the remainder of this presentation, we are going to be in the supervised learning space, where we're using labeled data to build prediction classification models. And the example that I want to describe with you today in that regard is work that was conducted by one of my former graduate students by the name of Whitney Shea. So her dissertation is entitled, or was entitled, Advanced Machine Learning Techniques for Temporal and Textual Analysis of Biomedical Data. And part of what she did as part of her dissertation work was develop a class of models within the realm of machine learning called natural language processing. And what natural language processing models deal with is the processing and analysis of written text. And so I chose this example for a variety of reasons. The first being that I think it's a really cool project. I think natural language processing has a great number of applications, both within the academic realm as well as outside of the academic realm. And then the other reason I chose this example is because I wanted to select something that didn't require a lot of domain-specific knowledge or jargon. So most of my work, as I mentioned, is in the molecular omics arena. And I didn't want the talk to be kind of weighed down with jargon. I wanted something that would be broadly, that would cast a broad net, and that anyone on this call could kind of roughly understand what I'm talking about. So with that being said, let's kind of jump into the problem. So here at the University of Kansas Medical Center, we have an NCI designated cancer center. In fact, it is a comprehensive NCI designated cancer center. There are only about 70 NCI designated cancer centers throughout the United States, and only about 40-ish of them have achieved the highest level of designation, which is this comprehensive status. Now, to retain that designation, every 5 years, the major grant that supports our cancer center through the National Cancer Institute goes up for renewal, okay? And there are a great many things that the reviewers and the NCI are looking for when they're renewing our status as an NCI designated cancer center. And one of them, though, is scientific productivity. So a cancer center has two broad operations. You have the clinical operations where patients are actually being seen and treated. And then you have the research operations of the cancer center, okay? So from the research standpoint, the scholarly output of the members of the cancer center is really important and instrumental to retaining that high level of designation that the University of Kansas Cancer Center has. So with that in mind, when we think about scholarly output, there's a number of different ways to kind of measure that. One obvious way of establishing scholarly output is your publications, right? So within the research arm of the Cancer Center, you have about 150 members of the Cancer Center, all researchers, most of them at the PhD level, that are conducting cancer-related research and publishing their findings in scientific journals. So to establish scholarly output in a 5-year period, what you could do is you could look at how many papers were published that were cancer relevant by University of Kansas Cancer Center members over that time period. Okay, what were the journals that they appeared in? What's the impact factor of those journals? Those are all ways of building a case that you have good scholarly output. So with that in mind, let's kind of think about how we might do that. So the way that has been done here at the Cancer Center historically and up until fairly recently is this has been a fully manual process. Okay, where there is a data scientist that's involved with the Cancer Center who would be given a list of Cancer Center names, okay, first name, last name, and affiliation of all Cancer Center members during a defined time period. So that could be a 5-year time period to coincide with the renewal of this grant. And that individual would take those names and would go to publication repositories like Medscape or PubMed and would type in the person's name and their affiliation. Up would come the PubMed IDs and publications from that individual. Those publications would then be used to create an Excel file. And that Excel file would then go to the program leaders. So there are 3 programs in the Cancer Center. And those program leaders would be tasked with reviewing all of the publications within that 5-year period from all of the members to determine whether or not they were cancer relevant. Because we don't want to take credit for non-cancer relevant papers, because again, this is University of Kansas Cancer Center. So we're doing cancer research. So that is a really exhausting and laborious process. It is also error prone in the sense that your definition or my definition of cancer relevant may be completely different. So there's a certain level of subjectivity to this, and it's very laborious, and it is a huge administrative burden when this needs to get done. So that begs the question, can we leverage machine learning and natural language processing to potentially automate this process? Doing so would have a lot of implications. Primarily, it would decrease the administrative burden that is currently a major holdup. So kind of with that in mind, here's the process and the way it's currently being done. This is just a copy of the figure that we were just looking at. What we wanted to know is whether we could step in and kind of automate this entire process. So could we create a tool that would take as input cancer center names, their affiliation, and the time period, and then through an API, automatically pull those publications from PubMed? And then could we use natural language processing to basically screen each one of those papers to make a prediction, to make a classification of whether or not the content in that paper was cancer relevant or not? Okay, so the objective of this overall research project, the broad objective, is to automate the process of publication, retrieval, and reporting to support the University of Kansas Cancer Center, to decrease the administrative burden. And to fulfill that objective, we kind of broke it down into two pieces. The first piece is critical, and it's critical to start with this piece first, because we need to know whether or not natural language processing can actually be used to effectively screen publications for their cancer relevance. The reason why this is important to start with, because if we can't develop a tool or a method that can do that, then there's no relevance, or there's no reason to actually invest the time and energy to creating a user-friendly interface that allows administrators in the cancer center to be able to retrieve the cancer relevant publications that are co-authored by KUCC members. So we start with objective one. So with that in mind, we need to think about what type of data do we need to actually build that prediction model, and what type of data do we need to evaluate how good our predictions or classifications actually are. So this is just kind of a high-level description of how a lot of supervised learning projects work. You begin with a full data set, okay? For us, that full data set consists of a long list of publications. It includes their title and their abstract. It also includes a label of yes or no that indicates their cancer relevance, okay? So for a long list of publications, we have the title, the abstract, and then a column in the Excel file, if you will, that indicates yes, it's cancer relevant, and no, it's not. From that full data set, we create what's called a training and a testing data set. The training data set is a vital part of this process. That's the data set where we use the labels, the yes or no cancer relevance, along with the title and abstract of each of the publications to see whether or not there are patterns that associate with whether a paper is cancer relevant or not. Now, in the case of written text, we're looking for keywords, right? For instance, if the title says cancer in it, there's a good chance that that paper is going to be cancer relevant. If the abstract uses terms like oncogene, oncology, tumor suppressor, BRCA1, BRCA2, there's probably a good chance that that paper is cancer relevant. So that's what we're doing. We're trying to use the text to see what those patterns look like. Now, I just gave you a few examples. The appearance and frequency of specific words can be used to discern those patterns. And then the patterns that we discern from the training data are then used as the basis of a classification model, so that when we obtain a new abstract for which we don't have the label of cancer relevant, we can look at the abstract, find the key terms, how do they appear, where do they appear in the text, and use that to make a prediction of whether or not the paper is cancer relevant. Now, to assess how well our model is performing, we need a testing data set. So the testing data set is a withheld, entirely independent data set where we have the exact same information as we do with the training data. We have the titles and abstracts of a set of publications, along with a label of whether or not they're cancer relevant. And so the reason we have this testing data set is we develop a model in the training data set. We then apply that model to the testing data, and then we check our predictions in the testing data set with the known truth of whether the paper was cancer relevant or not. That gives us an idea or an understanding of how well our model is performing to determine whether or not it's even useful going on to step 2 to create the tool to automate this entire process. Does that make sense? Okay. So let's talk about the data sets that we used in this particular experiment. So there were 2 data sets that we used, and I'm going to refer to the first one as the KUCC data set. So the KUCC data set was a collection of publications from the University of Kansas Cancer Center from 2015 to 2023. So these were publications that were co-authored by Cancer Center members during that time frame. And there are 7,436 publications that fit that bill. Now, because the University of Kansas Cancer Center is a matrix cancer center, okay, so people that have their faculty appointment at KUMC may or may not be affiliated with the cancer center. And of the people from KUMC that are affiliated with the cancer center, many of us conduct research in other areas. We also have an Alzheimer's disease research center here at KUMC. We have a kidney institute. And so if we look at the papers from 2015 to 23 that were published by cancer center members, we can kind of get a sense of what was the frequency of cancer relevant papers versus the frequency of non-cancer relevant papers, because cancer center members are also publishing in other areas. So as we look across these years from 2015 to 2023, we see that the majority of publications in any given year are cancer relevant, not unexpectedly, but there is a non-negligible fraction that are non-cancer relevant. Again, for the reasons that KUMC members are publishing in other areas, okay? So from this list of nearly 7,500 publications across the totality, about 4,400 of them were cancer relevant, and about 3,000 of them were non-cancer relevant. So that gives us the data that we need. We have our titles and abstracts of those papers, and then we have a label of cancer relevant or not. Now, the question that you might have is, what decided whether the paper was cancer relevant or not? Well, in this particular case, the yes or no reflects our own internal ways within the cancer center of assigning cancer relevance. So we have our own list of keywords. We understand, the administration and the leadership in the cancer center has their own way of defining cancer relevant. And so these data reflect our own internal ways of that assignment. To get another data set, which I'm going to refer to as the derived data set, what we did is we collected abstracts and titles of papers that were published in AACR journals. So AACR stands for the American Association for Cancer Research. And that particular AACR has a number of different journals that range from kind of basic cancer research to translational cancer research to epidemiologic cancer research. And that is important in that it reflects the expertise and areas in which KUCC members work. We have basic cancer researchers, translational, clinical cancer researchers, and we have epidemiologic cancer researchers. So we wanted to select papers that reflected the range of expertise, experience, and research activities of our own members. So we collected 11,785 papers from the AACR journals over the same time span that we did for the KUCC data set, so from 2015 to 2023. Now, in addition to having papers that are cancer relevant, we also need to have in our data set papers that are not cancer relevant. That proved to be a much more difficult task. It's easier to say something is cancer relevant than to say it's not cancer relevant. So the way that we did this was we looked at the major research centers and institutes at KUMC, and then we tried to select journals that are kind of flagship journals of that specific disease or that specific area to pull publications from. So as I mentioned before, KUMC has an Alzheimer's disease research center, and one of the flagship journals of Alzheimer's disease research is the Journal of Alzheimer's Disease. And so we select papers from that journal. Similarly, we went through various centers and institutes and tried to identify journals that other KUMC members might be publishing in to assemble our list of non-cancer relevant publications. Okay, so now we have two data sets. We have our KUCC data set, we have our derived data set. Now I'm going to describe to you kind of three scenarios that we used to train and test our natural language processing models. So the first scenario was we use the derived data set entirely. We take 80% randomly, we just randomly select 80% of the abstracts and titles, and they're going to be used as our training data set, right? To discover the patterns that determine cancer relevance or not, and then to use those patterns to build a model. And then we're going to use the remaining 20% to actually test how well our model is doing. So the key distinguishing feature of scenario one is that we use the derived data set to both train and test the classifier. Similarly, for scenario two, only the KUCC data set is being used for the purposes of training and testing. And then in scenario three, we kind of have a hybrid. We use the derived data set to train the model, and we use the KUCC data set to test the model. Now, there's kind of a key thing, and I don't really want to get into the weeds. This is not the presentation for this, but when we talk about text classification, there are really kind of two key methodologic pieces to this. The first is that written text is words. We need some way of numerically representing words. All right. So the first task that we have is to numerically represent the words in the title of a paper or the words in the abstract. And there are many ways of doing this. The two that we explored are called word embeddings and term frequency inverse document frequency. So TF-IDF, that looks for the appearance and frequency of certain words. So as you can imagine, in a cancer relevant paper, you might be seeing words like cancer, oncology, tumor suppressor gene, smoking, other risk factors for cancer. Word embeddings, and I'll explain word embeddings in a moment here, that is a numeric way of representing text that uses the semantic meaning of specific words. The second thing that we need to have after we've numerically represented our text is we need some type of statistical or machine learning model that takes as input that numeric data to discover the patterns and then to make a prediction or classification. So let's talk a little bit about word embeddings. So there are different ways of doing this. What we did was use BioBERT embeddings, and BioBERT embeddings is a way of representing each word in the abstract as a 768 dimensional numeric vector, where that vector, so if we have two words and they appear close in that vector space, it means they have a similar semantic meaning. So like the words property and house would appear close to one another in that 768 dimensional space because they mean similar things. Similarly, carcinoma and sarcoma, different types of tumors, we would expect them to appear similarly in that space. So here's just a brief look at the data. So we have our two different approaches for numerically representing the text, and then we have different machine learning or statistical models that we actually use to build the models. There were two different metrics that we used to assess performance. Without getting into the details, those two were F1 score and the area under the receiver operating characteristic curve. What is important for you to know is both of those metrics take on values between 0 and 1, with 1 indicating better performance. So you want a model to get you values that are close to 1. And so one of the things that we see here is pretty much uniformly across the board, TF-IDF, and particularly when we use support vector classification, tended to lead to the best performance. One of the other things that I feel compelled to mention is this whole meaningless F1 score. This meaningless F1 score, what that represents is if we just predicted every abstract or every paper to be cancer relevant, what would the F1 score look like? So what we would hope is that the performance of our models far exceeds what the meaningless F1 score would be for a given situation. So overall, performance is pretty good, especially in the derived data in scenario 1, maybe to a slightly lesser degree in the KUCC data set. And then the performance is, the least good when we train on the derived data set and apply it to the KUCC data set. But by, all intents and purposes, this is still pretty decent performance. And again, this just kind of emphasizes the point that, the support vector classification with the TF-IDF way of representing the new numeric text provides, the best performance. Again, with the derived data set, we're very, very close to achieving values of 1. So very good performance within the derived data set. So with this in mind, and we felt very encouraged that we were getting pretty decent results, Whitney then set out to create a user-friendly application that would allow administrators that are part of the Cancer Center to be able to seamlessly implement this without having to know how to code in R or Python. So she created what's called an R-Shiny application. And this is a fully automated app that will take as input the names of Cancer Center members. It will take as input a date range. You can also put the affiliation of those members. And what it will output is a list of publications that were co-authored by those members across a specific time period, along with the predicted probability that that paper is cancer relevant or not. So here's just an example all of these names are members of the Biostatistics and Informatics shared resource that I co-lead with my colleagues Byron Gajewski and Dinesh Mudarantankam. So we took all members of the BISR, we input them, and this is just a snippet of the data. So this is just an Excel spreadsheet that lists all the publications from 2020 to 2024 that were co-authored by members of the BISR. This is the title of the publication, the year it was published, the PMC ID if it was available, the PubMed ID if it was available, the authors of interest. So these would be members of the BISR, our affiliations, the full citation, and then this is what I want to draw your attention to. Columns I and J, these are the predicted probabilities of cancer relevance. So the closer it is to 1, the higher the predicted probability that that particular paper was cancer relevant. The closer it is to 0, that means that that paper was likely to be non-cancer relevant, or at least so our models tell us. The reason we have 2 columns is because we created 2 different models, one based on the derived data set and one based on the KUCC data set. So I want to draw your attention to this paper right here that I have highlighted. Both the KUCC data set and the derived data set predicted this paper to have a high probability of being cancer relevant. So if we actually look at that paper, let's just look at the title. Using Bayesian hierarchical modeling for performance evaluation of a clinical trial accrual for a cancer center. Yes, definitely relevant. You can read that. Cancer is right in the title. And then if you further read in the abstract, I promise you, you'll be further convinced that this is cancer relevant. Not surprisingly, it achieves high scores for both models. If we draw our attention to another one, this one here, that achieved a low predicted probability for both models, 0.03 and 0.12 respectively. If we look at that particular paper, and I'm just showing you the titles, the title of that paper is Prenatal Care Utilization Challenges and Facilitators for a Growing Latino Community in the Midwest. I'm not showing you the abstract because that would be too long, but judging from the title alone, probably I think most of us can agree, probably not cancer relevant. All right. So just to kind of summarize here, and then I'll turn it over for questions in the remaining 10 minutes. Just a brief recap. So the problem here is we wanted to apply our data science and machine learning expertise to help the Cancer Center expedite the process of publication screening for cancer relevance. And so our objective was to build a natural language processing method and an accompanying tool that would help to automate this process. We did this through the use of numerous different statistical and machine learning methods, as well as different ways of representing the text numerically. And our results showed that natural language processing does indeed have promise for determining accurately whether a paper is cancer relevant or not, judging only on its title and abstract. So there's a number of different avenues that we can take from here. We can consider what's called ensemble-based approaches, where the prediction from multiple different models is kind of combined into one prediction that borrows strengths from different types of models and mitigates their weaknesses. We can explore neural network architectures, and we can also try additional sources of data. As far as the actual tool that we've developed, one of the things that we're currently doing right now is what's called user acceptance testing. So we've created a beta version that we're having administrators try out to kind of help us identify any bugs or any issues that need to get fixed. What can we do with the interface to make it more user-friendly, and so on and so forth. So to that end, I'd like to give a special thanks of other people that were involved in this work. So again, this was led by my student, Whitney Shea, who's now a faculty member at Kansas City University. John Fife, Lisa Harlan Williams from the Cancer Center, Dinesh Mudarantankam, and Dong Pei from the Cancer Center were heavily involved in this. And I'd also like to thank K-INBRE, as well as the University of Kansas Cancer Center for their support and all the various data science things that we do. So with that, I'd be happy to take any questions on the work that I presented or data science in general. And again, just kind of thank you for your time.
That was really great. I've got to run to a comps exam, but I did want to ask one question about cancer relevance or otherwise other discipline relevance. What as you know, even other non-cancer basic science stuff is cancer relevant, such as vascularization of or DNA damage or things like that. How how well how general can a topic be, or does your algorithm miss anything that may be relevant but not have the term cancer in it?
Yes, absolutely. These algorithms are not perfect. There are a number of challenges associated with this. By the way, cancer relevance is a subjective thing. Um, what our cancer center considers as cancer relevant may not necessarily align one to one with some other cancer center. So we have our own ways of defining cancer relevance based on our experience of going through these renewals and knowing what passes the sniff test or not. There's been things that I think we have tried to argue that we feel are cancer relevant, but obtain pushback from the NCI, them not viewing it as cancer relevant. So part of it is an ongoing calibration with what passes the sniff test versus what doesn't. The other thing that complicates this is our understanding of cancer, what drives cancer, risk factors for cancer, how it develops, how it progresses, is evolving as we speak. So things that may not have been considered as cancer relevant 30 years ago are today considered cancer relevant. Obesity is a good example of that. Obesity is poised to overtake smoking as one of the biggest risk factors for cancer over the next 20 years. 30, 40 years ago, it might not have been considered as significant of a risk factor as it is today. So it's a constantly moving target, which is why this is not a one and done type of situation. These models are going to need to continue to be developed and trained as we move forward and as our understanding and definition of cancer relevance changes. So you raise a really good point. I don't know if I answered your question, but
Yeah, no, you did. It's based. Yeah, I'm coming. All right. Thank you.
thanks, John.
I have a question. Do you mind please to share your screen again and go to the result table, please?
Um,
And thank you, Devin, so much for your great work and your presentation in general. I am just wondering, to compare between the AUC and the F1 score, why there's a big difference between the two, since both reflect the performance for both classes, they are relevant or not relevant. Like the AUC is 0.977 and the F1 score is way low for all of them.
mm-hmm. Yeah. So the AUC, when we calculate that, that is calculated as a function of the receiver operating characteristic curve, which is calculated based on the sensitivity and specificity, right? Okay, so the big things those are the two major features that are going into our calculation of the area under the curve. With the F1 score, that's a function of precision and recall. So it kind of, I think what may be driving the disparity that we see between the AUC and the F1 score is where the weight is being placed on the various metrics that are being used to actually calculate that score. So one thing I can tell you from especially scenario 3, where we trained the model based on the derived data set and then tested it on the KUCC data set. So we have in the Cancer Center a much more liberal definition of cancer relevant than I think what is reflected in the derived data set. What I mean by that is in the Department of Biostatistics and Data Science, a lot of the methods work that we do, statistical methodologies, machine learning methodologies, have broad scientific applications. And we would, in our progress reports, consider them as cancer relevant because a lot of times later down the line, we are applying them to cancer relevant studies. Okay, so we would count them as being cancer relevant. Whereas the way we constructed the derived data set, it really represents very hard definitions, right? We took papers published in cancer-related journals, papers not published in cancer-related journals, and that forms the basis of the data that we used. So A lot of times what we saw for scenario 3 is that we had papers, when we applied it to the KUCC data set, we had false negatives. So papers that we scored as being cancer relevant, but were being predicted to be non-cancer relevant. At any rate, the reason I say all of this is that the performance was not equally balanced when looking at sensitivity and specificity, or precision and recall. So I'd need to maybe dig a little bit deeper to give you a more firm answer on the disparity between the AUC and the F1 score, but I think it might be driven by, again, the exact measures that are being used to calculate that score and where the weight is kind of being placed.
Thank you.
Yep.
Great talk. I had a question where, oh, can you hear me? Sorry. Great talk.
Yeah, I can hear you.
So you mentioned that an app was developed based on this research, and I was wondering if you've seen any great impacts on the community that have used it. So any users who have spent time looking on this database searcher, do you think it's pretty useful for them? And
Julie,
how would
that's
you
a
measure
great,
that, I guess?
that's a great question, Julie. So the short answer to your question is not yet. So Whitney just defended her thesis like a month and a half ago. And so we do have the app created, and we have started kind of what we call beta testing. So just giving it to a small number of people and having them kind of work through it to identify bugs or issues that we need to correct on our end. But we have yet to really fully understand the full impact of this. I think we'll probably have a better understanding sometime in the spring, which is when we typically do our progress reports, to understand the administrative burden that this offsets. So I think it is overly ambitious to think that this application will fully, even though I use the term fully automate, I think it's overly ambitious to think that. I view this as just a tool to help the decision making. So if you have papers that are scored with really high probabilities or really low probabilities, maybe you can feel comfortable about those predictions, but you still may need to look at the ones that are intermediate, right? Where the predicted probability ranges from 40 to 60%. Now, it's difficult to know in advance how many of those are going to fall within that range in any given year. And, the full impact of how much time that this offsets from the administrators that use this has really yet to be determined. But we should know, again, like sometime this spring. So sorry, the short answer to the question is no, but we're still working on it. Thank you.
Thanks.
We've got a hand raised from Michael. I think you're good. Go ahead.
All right, thank you. I have a slightly more technical question about the term frequency and verse document frequency implementation that you did. Could you switch to that one slide that you were showing earlier where you had the TD-IDF explained? Basically, my question is going to be, the TD-IDF is a bag of word method. Did I get it out of my mouth? So you had to do some tokenization and some vectorization there. And I've been playing around with these methods as well. And I understand that your final graphical user interface that was being used, that was just a shiny user interface that was obviously done in R. But I found that a lot of the TF-IDF implementations out there, they basically all gather around scikit-learn or some other Python package. So I was wondering what kind of library was used in the background in order to do the count vectorization or the bag of word tokenization.
I believe it was scikit-learn, but you know what? I would definitively need to reach out to Whitney, as she was the one in the trenches here that was doing all of this work. But I believe that's what she used.
Yeah. It's as far as I know, it's the best developed currently, but there are lots of alternatives popping up everywhere. So I was just wondering what
I'm
you were
about 95% sure it was scikit-learn.
All right, thank you.
Thanks, Michael.
Can I ask one more question?
Of course.
Yeah, thank you. like for the slide about like the data and show the probability, where did this probability come from?
Do you mean this one?
No, like the data that's showing the data.
This one?
Yes, this one here. There's a
Yeah. So where did the
probability.
probabilities come from?
Yes, please.
Yeah. So the probabilities that were being shown here came from the models that I described in scenario 1 and 2. So the sorry, I'm going in the wrong direction. So we had two different models that were built. So both of the models use the TF-IDF support vector classification approach, but one was developed using the derived data and one was developed using the KCC data. So the predictions, the predicted probabilities that are being shown in columns I and J were when we took those models and we actually applied it to these data. And by data, I mean the title and abstract for these specific papers. I don't know if that answers the question. So these are the predicted probabilities for those two different models. We have the derived model.
From the, yeah.
So the derived
like,
model, yeah, go ahead.
I might try, but as I know, the support vector machine doesn't like provide probability.
So it was
for-
support vector classification.
Yeah,
So
I might be wrong.
sometimes we might round that. So we are predicting the probability, and a lot of times we wind up just providing an actual class label. So we discretize it into, one group or the other. But underlying that, there's a mathematical model that actually can be used to get a predicted probability. A lot of times we just assign it to the group that has the highest probability, and that's what we see at the end of the day. But if you pull back the sheets a little bit, what we have underneath that is actually a probability, and that's what I'm showing here for both of these models. So one was developed using the derived data set, one developed using the KCC data set.
Thank you so much.
Anything else?
This is a more general question for me as an undergrad looking for grad school opportunities and for any other undergrads in general. How would you describe the difference between, say, computational biology or data science and bioinformatics? And does the data science core at KU largely reflect more bioinformatics kind of projects versus molecular dynamics simulations in computational biology labs and things like that? Curious to hear what your knowledge in that is.
I can take a stab at that. It's a little bit of semantics. And things are moving quite quickly. So it was data science for a while, was kind of like supposed to be all encompassing. And then AI became kind of the buzzword. I would say in general, AI doesn't really exist as it's promoted. The tricky one is computational biology. Computational biology is kind of pushes you a little bit more into the modeling side of things. So usually when we're talking computational biology, you're like analyzing data, but also building some sort of mathematical model on top of it. But it overlaps very, very heavily with data science to the point that they're very, very similar to each other. In terms of like graduate schools, you'd probably be looking at all of them at this point because it kind of depends on when the graduate program was developed and kind of where it's positioned as to what you'd be looking at. See, there's bioinformatics. Bioinformatics would be like the kind of the older term at this point. But they're all going to be doing very similar things. I think the bigger thing you'd want to focus on, like if you're looking for graduate school, would be more of like, so let's say you're looking for a PhD program and you know that you are interested in, say, doing something where you're going to integrate multiple data types. You would find a institution that has, say, 3-4 PIs there that are working kind of on that general idea and general approaches. I think generally the technical end of data science, and Devin can always jump in and kind of correct me on this as well. I generally find the technical part of it is a very interesting and important part, but there's also, you have to look at both the domain and the technical side and put those two together. So that's really what you're looking for is, are the scientific questions that you're interested there? Are you getting the technical training that you need to be able to approach that? And we're always happy to help you look at them right now there's like 4 or 5, I would say, major schools out there that really like are attracting a lot of students and have a lot of resources. There's a lot of kind of like mid-level schools that are developing or have developed programs that are kind of all over the place. And I would definitely be looking for something that is obviously in person with a PI and established lab. The 4+1 is probably kind of a different type of approach, just to kind of like give you the signpost. So PhD program would be like full-on training. That'd be preparing you for either an academic career or possibly an industry career, depending on what you're interested in. Or we're talking things more like the 4+1 type programs and other like 4+2 type 6-year training programs. Those are almost always going to be training you for going into industry and being a little bit more focused on practical skills and like internship type skills to get you experience with going into a biotech, let's say, or a pharmaceutical company or related industries. So they're kind of all over the place. I would say right now, most people are kind of settling on AI as the terminology for all this, just because that's ChatGPT has really popularized that. There's still kind of data science. There's also like data engineering, which is another kind of like adjacent field as well. So that's a little bit more practical in terms of like having to put data together in ways and grab data from different places. So it really depends on both what your career goal is, the type of domain training you're needing, and then also the history of the program that you're applying to. So it's complicated, it's kind of the summary, but I'm more than happy to sit down and go over graduate programs with you if you're interested, or at least give you some ideas of things to look at depending on what your specific interests are.
Okay, I appreciate it. Thank you so much for that.
Yeah. What school are you at, Julie?
I'm at Wichita State. I'm a senior.
Okay. Yeah, I'm more than if you want to set up a meeting, I'm more than happy to give you some ideas of places to look. Just reach out to me. Next week is a little crazy, but I can make something happen.
Yeah, for sure. Thanks.
Yeah, sit down, chat about the different types of programs, what you're interested in, and go from there.
I do want to make sure that everyone knows that, yeah, we're well over time. So if anyone needs to hop off, I see a few participants already have, no big deal. But I also saw Michael still has a question. So if you're willing to stay on, happy to, but totally no pressure at all.
Yeah, for all the trainees out there, just to kind of jump off of Julie's question, all the leadership for Data Science Core is more than happy to sit down with students and discuss both what you need to prepare for a career, how to do it, graduate programs, anything you need in terms of like wanting to learn about these sorts of things. More than happy to sit down with you and share some Zoom time. We'll also be at the K-INBRE Symposium in January. So if you're attending, I'm more than happy to sit down and have a cup of coffee with you and talk about all the cool stuff you can do.
That'd definitely be a great time to chat. Yeah, I was going to put a plug out there, not for the symposium necessarily, because I think all of us already know about that, but just in general, that the Data Science Core is not only available on this Zoom call. There are incredible resources, top to bottom, for anything that you might need in the state of Kansas and beyond related to data science. They're very connected and resourceful and incredibly competent faculty members. So they can get you connections kind of wherever that might be needed.
Yep.
Michael, did you have one more question you wanted to ask, or are you all set?
No, I just wanted to shamelessly use this opportunity, since there was the question about graduate student positions, to mention I would have one more graduate student position available right now. I'm actually recruiting for one where we're actually using various bioinformatic methods, including machine learning, on some organelle data sets. So if anybody knows a senior who is about to finish and is interested in starting in spring and January 2025, I have this one position available. Please send them my way. Thank you.
Awesome. Well, if there are no leftover questions, or even if there are, I think we'll close it out for today, since it's been a little bit over time. And yeah, if anyone wants to reach out to Brad and Devin, their contact information is on the initial flyer that I sent out. And then there'd be like a million other ways that you could get it. You can call me, you can call Hayata, you can email us, whatever. So we're happy to form connections wherever needed.
Claire, could I say one last thing really quick? This
Of
is
course.
in response to
Yeah.
Anas. Anas, am I pronouncing your name right? And honestly, if you're using R, there's a function called predict.svm in the same package, the E1025, whatever it is, package for fitting SVMs that will allow you to predict the probabilities. I think it uses Platt scaling. So you just apply it to the object that you have created from when you actually fit the SVM model. So predict.svm, and it's in the same package. Yeah. Sorry, just wanted to answer that, tie that knot up.
Thank you so much.
All right, thanks everybody. And Julie, definitely feel free to reach out and we're more than happy to chat.
Thanks, everyone. I'll get this recording up on the website. Take care.
Thank you.
Bye. Thank you.
Bye, everyone.